Okay, we're going to talk about enthalpy, and more specifically, we're going to talk about enthalpy change. Now, what is the enthalpy change? It's defined as the energy change of a reaction, but measured at constant pressure. So that's the strict definition of what enthalpy change is. We don't really, most of the time when we do reactions, we do them at constant pressure. But just, you imagine you've got this reaction, you've got like magnesium hydrochloric acid, giving you magnesium chloride and H2. Well, how would you normally do that reaction? You do it in a beaker, yeah, and you wouldn't have a lid on it, so all the hydrogen gas that got given off would release, and the pressure would be constant. Generally speaking, we don't do reactions at constant volume. At constant volume, if you put a lid on that and sealed it in so nothing could get out, yeah, then the pressure would increase. And if you measure the energy change at constant volume, it would be slightly different than the one measured at constant pressure. In actual fact, you'd get slightly more energy out if you did it at constant volume, because this hydrogen gas here has to do a bit of work against the atmosphere when it comes out, and so you lose some of the energy in that way. But don't worry about that. But they do occasionally ask what is the definition of enthalpy, and it's at constant pressure. Okay, now we can't, if you want to measure the enthalpy of sodium chloride, for example, at 20 degrees C, you can't measure the enthalpy. The only thing you can do is measure changes in enthalpy that occur during a reaction. So if we just see what this looks like on a graph. So if we have a graph here, let's say we've got let's go an exothermic reaction. This reaction is exothermic, so this is good. Okay, and we're going to put energy on this axis. Now I should really put what kind of energy. I'm going to say the chemical energy. That's what it is really, but most people don't usually write that there. It's chemical energy. So we start off with the magnesium and the HCl up here. Now this gets hot, this reaction. So you get some chemical energy is converted into thermal energy. So that means the chemical energy is going to go down. So that's what we've got there. We've got MgCl2 and H2. So there's less energy in the products than in the reactants. So I'm going to get rid of that. I'm not going to call it energy. I'm going to call it enthalpy. Okay. And we're doing this at constant volume. So this is enthalpy on this axis. The enthalpy has gone down. And so we say, right, well, the symbol for enthalpy is H. Whenever you have a change in something, it's always delta, isn't it? You use that in maths, I think, probably. When you're doing gradients and things, so delta H. So the change in enthalpy here is negative. Why is it negative? Because these products have got less enthalpy in them than the reactants, and that's been turned into thermal energy. So one little confusing thing at first is that an exothermic reaction, some people instinctively think it should be the way around. An exothermic reaction, the enthalpy change, delta H, is negative. And for an endothermic, obviously, delta H will be positive. Okay, so how do we go about measuring the enthalpy change of a reaction? Well, usually we do something, kind of experiments called calorimetry, okay? We do calorimetry experiments. And calor, anything with that in it is going to mean something to do with heat. Okay, so let's say we want to find out the delta H, the enthalpy change for this reaction. So we're going to get methanol, burn it in oxygen to give CO2 and H2O. It's going to be 2 H2O there. So that means you are going to need 1.5 oxygens, I think. To balance it 1.5. So we want to find out delta H for that reaction. And we're going to measure it in kilojoules. Kilojoules, and we're going to measure it per mole of methanol. So we're going to do kilojoules per mole of methanol. Now, what equation do we need for this? You've probably come across this at GCSE physics, I know. And right, so it's the equation we're going to use is Q is equal to MC delta T. So this is the quantity of. So what we're going to do is we're going to get a copper can, because it's a good conductor. Okay, so we're going to get a copper can rather than a glass beaker. We're going to put a spirit burner underneath that. We've got methanol in there. And I'm going to put in there 50 centimeters cubed of water. And put a thermometer in there. And we're going to measure the temperature at the start and the temperature at the end of the reaction. How are we going to find out the mass of methanol that we burned? Well, the way we're going to do that is we're going to weigh this spirit burner, weigh the burner before, and also weigh it after we've heated up a little bit of water. That's how we're going to do it. And the difference in mass is going to be the mass of the methanol which has been burned. Okay, so let's see what these things stand for then. Okay, so Q is the quantity of heat released. And that's going to be measured in joules. M, right, that is going to be the mass of the water that we have in the can. And don't forget that 1 centimeter cubed of water weighs exactly 1 gram. Right, delta T, that's the temperature change. In degrees C. And C, if you remember from physics last year, C is the specific heat capacity of water. And you're always given that value in exams, and it's usually quoted as 4.18 joules per gram per degree C, or per Kelvin, because although Kelvin and degree C, they're not the same, an increase in 1 Kelvin is the same as an increase in 1 degree C. So now let's just think, what is the specific heat capacity? Well, it's the energy required to increase increase the temperature of 1 gram of water by 1 degree C. That's what the specific heat capacity of water is. And you probably, last year, you did the specific heat capacity of metals and all sorts of things. And just be a little bit careful there. I think in physics, you usually measure that in kilojoules. Sorry, you usually measure this in joules per kilogram. Okay, we're measuring it in grams, usually in chemistry, not kilograms. So I think you should quote this 4,200 joules per kilogram of water. Okay, so let's do some get some results for that experiment, and let's see. We're going to work out delta H. Oh, by the way, is this heat released here? Is this the delta H per mole? Well, it's not, is it? Because this is, we need to convert that. So we need another equation. We need delta H, beg your pardon. Delta H is equal to Q divided by the number of moles of methanol that we've burnt there. Right, so let's put some numbers into that and work it out. Okay. So, right, if I roll this down a little bit, I'll just write the equations down so we can see them again. Don't forget Q is equal to MC delta T, and also delta H is equal to Q over moles. Now, we're going to say the mass of the water in the flask, and the mass of the water was 50 grams. We had 50 centimeters cubed in the calorimeter. We'll say that the temperature change during that reaction, well, the temperature went up by 23 degrees C, an increase. We're always given the specific heat capacity of water, that's 4.18 joules per gram degrees C. And the mass of methanol burnt, and remember we did that by weighing the burner before and after, was equal to 0.47 grams. Put the numbers in, see what we get then. Q is equal to 50 times 4.18 times by 23. That's equal to 4,807 joules. Now we need to use this equation next, don't we? But we need to work out the moles of methanol, and we need to work that out from the mass of methanol. So we're going to have to do here moles methanol burnt is equal to mass over MR, 0.47 over 32 MR of methanol gives us 0.0147 moles. So now we can put this number of moles into this equation here. Okay, so delta H is equal to Q over moles is equal to 4,807 divided by 0.0147. I'll just do that in a calculator, and that is that is 327,006 joules. Right, we want to express that as kilojoules, so that's going to be 327 kilojoules. Right, I've been a little bit naughty there because we've only given some things to 2 sig figs, okay, and so I should really say 330 kilojoules. And because it's exothermic, I should not forget to put in that minus sign there. And they will actually knock marks off if you don't do that. So that is the answer to our question. The answer then, the enthalpy change occurring when you burn 1 mole of methanol, you get 330 kilojoules per mole of energy out. That's the enthalpy change. Now, if you compare that to a textbook value, you will see that I think the textbook value, so this is our experimental value. And the textbook value is minus 700 and 26. So our experiment, we are way out. Okay, why are we so out? These kind of experiments always give bad results when we do them in the school lab. Well, if you can have a look at the apparatus here, we're presuming that all of the heat from the burner goes into the calorimeter. It won't. A lot of it will just go into the air. We've got massive heat losses, so it's a very inaccurate experiment. Now, you can do these experiments a lot more accurately. You can imagine you could improve the accuracy quite easily by putting a lid on the calorimeter, putting some kind of insulation around the calorimeter, putting some kind of shield to stop drafts. You could improve it fairly easily. You can improve it a lot by putting it into a into a completely sealed environment. That's something called a bomb calorimeter. Okay, so you don't need to know the experimental design or anything, but you just need to know that if you want to do this accurately, you could do it very accurately, and you do it in a bomb calorimeter, and you would reduce all those heat losses and you'd get the correct answer. But just be aware that when we do them, we're going to get not brilliant results. Okay, we'll leave that there.